Hi everyone, this video will introduce the basics of dynamics at physics A level. That is Newton's laws, F equals ma, W equals mg and resultant force calculations. Some of this you will have seen at GCSE, but the calculations and explanations required are more difficult. Enjoy the video. Okay, the first thing we need to do is to distinguish between kinematics, which is the previous topic, and this topic, which is dynamics, because these two are very closely linked. So we could distinguish them by defining kinematics as the description of motion. So this is velocity, time, and suvet. And dynamics is still motion, but this is explaining the motion in terms of forces. So what we tend to find is a lot of exam questions in particular have these two topics linked together. So it's quite unusual to find just a kinematics exam question or just on dynamics. So we're going to consider the motion, how it moves and why it moves in terms of the forces. Absolutely fundamental to this is Newton's laws, first, second and third. So you will have seen these at GCSE, hopefully. They are really, really important. You've got to know these. And more importantly, well, just as important, you have to be able to apply them as well. So make sure you write these down and you make little posters or flashcards or however you're doing this in your revision. You've got to know these. So just to clarify, so first law, objects will stay stationary or move at constant speed unless an unbalanced force acts on them. So we could say a resultant force instead. If we just say a force, that's probably not true, because there's usually more than one force, so zero resultant force. Newton's second law, students quite often just say F equals ma. They've remembered that from GCSE, but that probably won't get you a mark at A level. So we need to think, well, what is the relationship here? Mass we assume is constant, so the force, in particular the resultant force, is proportional to the acceleration, or the other way around. So the acceleration produced by an unbalanced or resultant force is proportional to the force. That's the key idea. We could also add that it takes place in the same direction, but hopefully that's pretty obvious. If you push an object away from you, it should travel away from you in the same direction. Newton's third law, very often GCSE students remember this one. This won't get you any marks at A level, so we've got to make this a bit more sophisticated. We imagine two objects, object A and B, and if object A exerts a force on B, then B will push back, exerting an equal and opposite force on A. So that's how we need to phrase it. But bear in mind, we're not necessarily just talking about a solid single object. It might be a collection of objects like a body of gas, as we will see. Also, we need to be clear of one of the similarity and one of the difference for this Newton's third law pair. So they must be the same type of force. So for example, if you have a gravitational force, one object acting on another, then it will be the same gravitational type of force of the second acting on the first. Importantly, they must act on different objects. This is really, really important. If we don't understand that, and if we just say that all objects have an equal and opposite reaction force on the same object, well, nothing would ever move in the universe. So they are acting on different objects. That's really, really important. Okay, so something that you have to do at A level, and we'll look at this in more detail in the next video in this series, is explaining motion of everyday scenarios or possibly rockets or whatever it might be with reference to Newton's laws. So this is something really quite difficult. This tends to be longer response questions, so this takes a lot of practice. So we'll just look at a few simple examples. If we have an object placed on a horizontal table, then how do we explain that in terms of Newton's laws? Well, the weight is acting downwards. There's going to be a contact reaction force of the table pushing upwards, and these two forces will be the same size, acting in opposite directions. So the resultant force will be zero, so no motion according to either Newton's first or Newton's second law, because we could use both of those laws to explain this situation. The second one, if you can imagine an object, so not a rocket, but just something like a tennis ball or a lump of rock or whatever it might be, an asteroid, that's been projected into space, into deep space, then what is its motion? So we're a long way from any gravitational field. There's no thrust or propulsion from the object itself. So it will just continue at constant velocity forever, or until it comes into contact with another force. So if it comes near a planet or a star, whatever it might be, then it might be affected by the gravity. So this is a really counterintuitive idea. We don't see this day to day. We just are used to seeing things slow down after we've given them a push, because there's always the effect of friction. So if you remove friction and remove gravity, then objects will continue moving at constant velocity according to Newton's first law. So what about rocket propulsion? So why does the rocket go up when we fire a load of gas out of the bottom? So rather than one object and object A and object B, we can imagine object A is the rocket, but object B is the collection of hot gases rather than a single object. So the gases are being forced downwards. So object A, the rocket, is pushing downwards or creating a force on the hot gases acting downwards. Therefore, the gases create an equal and opposite force on the rocket acting upwards. So this is how we get our lift. So this is the basics of jet propulsion and rocket propulsion. This is Newton's third law. Right, so hopefully also a recap of GCSE F equals ma. You will have seen this before. Really, really important formula. We've mentioned it already in relation to Newton's second law. We need to be able to use this in a whole range of contexts, and not just in dynamics questions, but all the way through the 2-year A-level course. This will come up again and again, so it's a really important formula. And as we've said before, basically it's force is proportional to acceleration. So the bigger the force, the bigger the acceleration. So we've got force in newtons, mass in kilograms, and acceleration meters per second squared. And this also allows us to define the newton. So we know the newton is the unit of force, and the way we define it is by thinking if we have 1 kilogram and it has an acceleration of 1 meter per second squared, then the force that is needed to create that acceleration is 1 newton. So 1 newton is 1 kilogram meter per second squared. So this is probably not something you've seen at GCSE, and it's really important. That is a definition that you'll need for the exam. So a nice simple example, if we just have one force, then it's pretty straightforward. So if I know the mass and I know the force, I can rearrange F equals ma to make A the subject, A equals F over m. So in this case, 30,000 divided by 10,000 is going to be 3. Now, whether that's positive or negative depends on our reference. And in fact, the object, the lorry could be moving forwards, and this could be a braking force, so this could be a deceleration, which is the most likely scenario. But it could be accelerating to the left, it could be accelerating backwards. So without extra information, we don't know what's actually happening in this situation. So bear in mind this idea of positive or negative is up to us, really. We just have to decide which direction is positive and then stick to that convention. Another formula you will have seen before, W equals mg. This is basically F equals ma. It's a particular case of F equals ma. And hopefully you can see the similarity because W is a force, that's the weight, m is obviously mass, and g is the acceleration due to gravity. So at GCSE we assume this is 10, but at A level you would use 9.81 meters per second squared. So this is going to vary depending on the gravity of the planet or the moon that we are looking at. So we assume the average value on the surface of planet Earth is 9.81. On the moon it's going to be much lower, 1.6. The reason why is because the moon has a smaller mass. Not just because the moon is smaller, it is smaller, but it's because it has a smaller mass. So it's approximately a sixth, I think, yeah, around about that. So we have the weight, that's going to be a force, and that will depend on the strength of gravity. So m, the mass, never changes. It doesn't matter where we go in the universe. The mass is the amount of matter. That is a fixed value unless we start approaching the speed of light. But weight is a force measured in newtons. So we've got to make sure we get these two clear in our head. And very often in day-to-day life, people get these mixed up. They say they've got a weight of 60 kilograms, which is obviously incorrect. So make sure you've made the distinction between these two. They're different things. Let's have a look at some calculations. So the basic calculation, these are GCSE ideas. W equals m times g. That's pretty straightforward stuff. So for example, if I have a 10 kilogram mass on Earth, it's going to have a weight of 98.1. On the moon, it'll have a lower weight. So this is, as we were saying before, the mass doesn't change, but because the strength of gravity has reduced, then the weight will be smaller. Right, the final thing we need to consider is resultant force calculations. Now, you might have done some straightforward examples of these at GCSE, but at A-level they tend to be quite a bit more difficult. So let's have a look at these two examples. So in both cases, we're going to try to find the acceleration given the information shown. So let's have a look at the one on the left first of all. So we've got a force to the right of 6,500. We've got a drag force to the left of 800. So the first thing I need to do is to calculate the resultant force. So we could assume to the left or to the right it's positive, but it makes sense. We assume it's moving to the right, so let's assume this side is positive. So the resultant force is 6,500, take away 800, and then we need to divide by the mass, having rearranged F equals ma, and we can get the acceleration. So you might have got something as difficult as this at GCSE, possibly. This would be one of the more difficult questions. So that would be a standard, fairly straightforward one at A-level. Slightly more difficult is if we think about a vertical scenario. You might have a lift where we've got a mass and we've got the tension in the cable, and you're asked to find the acceleration. Now, a lot of students would make the mistake of just thinking 7,000 is the only force acting. But clearly we have the weight as well, even though the question may not have stated that. So if we have anything to do with vertical motion, so planes and helicopters and elevators and so on, we must calculate the weight. So we can calculate the weight, mg, that's straightforward. So we could actually draw an arrow here if we wanted to. And then we need to find the resultant force. So again, we don't know whether this is moving up or down. So I've assumed upwards is positive. So 7,000 take away the force acting downwards, the weight, 9,810. And then divide by the mass. This is going to give you minus 2.81. So again, as in the previous the example a couple of slides previously, we don't actually know what's happening here. So this could be accelerating downwards because the weight is larger than the tension, or it could be decelerating upwards. Either one could be possible. We don't know without further information. Okay, slightly more complex, and this would be getting a bit more kind of A-level typical standard. So we've got a helicopter, we've got the mass, and we're told the upward acceleration, and what is the thrust required to provide that acceleration. So again, a common mistake would just be to calculate m times a, and think that's the answer. Well, that will be the resultant force, and that's not the final answer. So it's a little bit more complex. So F equals ma. Remember that F is the resultant force. It's not just one or two forces, it's the overall resultant force. So T is bigger than mg, so T minus mg will be the resultant force. So this is quite an algebraic approach, but it's better doing it this way rather than just calculating lots of numbers and then trying to guess how to put them together. So make T the subject, so that's what we're trying to find. So minus mg becomes plus mg, and then we know all the values, so the mass is the same in both of these expressions. M times a, that's the mass times the actual acceleration, plus m times g, which is the weight. Add these two together, we get the thrust acting upwards. So you could imagine that the thrust is doing two things. It's got two jobs to do. It's got to balance the weight and also provide the resultant force m times a. So the thrust has to be large. It's got to be the sum of these two things in order to give us this acceleration acting upwards. Good, right, I hope that was useful. So the next thing I suggest you do is find the next video on YouTube, which will be looking at forces in free fall and also looking at some longer response questions, because the dynamics topic really lends itself to longer response questions in all exam boards. So that's definitely something you need to practice. I can also recommend you check out payhip.com, grade A physics. So we've got more videos like this, lots of questions with work solutions and quizzes and progress tracking and lots of other information there. Some of it's free, some of it's paid, but definitely worth checking that out. Great, see you next time.